Good evening, our dear listeners, and welcome to today's class. Today, we will be looking at a concept in mathematics and statistics called regression. What is regression? In regression, the interest is to predict the value of a variable from the value or values of other variables. Trying to understand or forecast the value of a particular variable from the value or values of other variable, you are doing regression. And then the variable whose values you want to predict or forecast is called the dependent variable or the response variable or the outcome variable. You call it what? The dependent, or you call it the outcome, or you call it the response variables or variable. But those other variables that you are using to predict or forecast the value of this response variable is called independent variable or explanatory variable or controllable variable. You call it independent or you call it controllable or you call it explanatory variable. Explanatory variable. Some real life explanation or examples of a regression could be a situation whereby you want to look at the growth of, say, maize planted in a farm based on the values of the quantity of fertilizers and the volume of rainfall in that particular place. So the growth of the maize is a dependent variable in this experiment, while the fertilizer and then the volume of rainfall are the independent variable. So you are trying now to predict the growth of this maize based on these two variables called the fertilizer and then the quantity of rainfall. Consider also a situation whereby you are looking at the performance of a student based on the person's intelligence quotient, number one, based on the number of hours of study of that student, and equally based on then the kind of reading groups that that student has. In this context, you are doing regression, looking at the score of the student or performance of the student as the dependent variable, and looking at the number of hours of study, the kind of reading group that the student has, and then the intelligence quotient as the independent variable. In that situation, you are doing what is called regression. And of course, there are two kinds of regression in terms of the number of variables, in terms of the number of independent variables involved in that regression. So we have what we call simple regression and what we call multiple regression. Have what we call simple regression, simple regression, and what we call multiple regression. Multiple regression. In simple regression, only one explanatory variable is involved. For instance, looking at the growth of what maize based on the quantity of a fertilizer. The only independent variable involved here is fertilizer. So in that case, we have what we call simple regression. But in multiple regression, more than one independent variable are involved. Be it two, be it three down the line. They are falling under what we call multiple regression. For instance, you are looking at the growth of the maize still, but this time around, you are using fertilizer. You are equally looking at the volume of rainfall. You might equally be looking at the intensity of sunshine in that particular place. So there are more than one independent variable that you are using to predict the growth of what of maize. Like we earlier explained in the scenario of the performance of a student, you are looking at the performance of students based on the number of hours of study alone. You are talking about simple regression. But when you are talking about the performance of a student and you are looking at the number of hours of study, equally the number of study groups that the student has down the line, you are discussing what is called a multiple regression. So this is the different kinds of regression that exists in terms of the number of independent variable or explanatory variable involved in the experiments. We equally have different kinds of regression that exist based on the nature of the relationship between the dependent variable and the independent variable in that particular research. And under this situation, the two kinds of regression we have is what we call the linear regression. Linear regression. And then what we call the non-linear regression, or what we call the curvilinear regression. Non-linear regression. Non-linear regression. Under the linear regression, permit me to remove what came up on my phone. Under the linear regression, the relationship that exists between the dependent and the independent variable is represented with linear model or with linear equation. However, under the nonlinear regression, we represent the model or the relationship that exists between the dependent and the independent variable or variables with a nonlinear model or a nonlinear equation. A way of buttressing what we earlier had said, classifying regression in terms of the number of independent variables involved. We have what we call the simple regression and we have what we call the multiple regression. But then classifying the regression in terms of the nature of the relationship that exists between the dependent variable and the independent variable, we have what we call the linear regression and what we call the nonlinear regression. And like I earlier had said, in the linear regression, the nature of the relationship that exists between them are represented with a linear model or a linear equation. However, for the nonlinear regression, the model or the equation is represented with a nonlinear model or a nonlinear equation. However, what makes the topic of our today's word class is the linear regression. So we are going to begin with what we call linear regression. So permit me to wipe the board and then write the linear regression. The linear regression. linear regression. In the linear regression, like I earlier had said, the nature of the relationship that exists between the dependent and the independent variable is represented with a linear model or a linear equation. And under this linear regression, we equally have two kinds of regression: the simple linear regression and the multiple linear regression. So here we have what we call a simple linear regression. Simple linear regression. And then what we call the multiple linear regression. The multiple linear regression. Do remember that when we talked about simple regression before, we said it's a kind of a regression where there is only one explanatory variable. So where we are now saying simple linear is a kind of linear regression where we have only one explanatory variable. But in the multiple linear regression, it is a kind of a regression where we have a kind of linear regression where we have more than one explanatory variable. So we are now going to show what we mean by the model of a regression. And what do we mean when we say the model of a regression? We are talking about a mathematical expression that represents a real life situation. That is what we mean by model. So we should be talking about the model for simple linear regression and the model for multiple linear regression. Model, a mathematical expression that represents a true life situation or a real life situation. So I will now go and write the model for simple linear regression. So you permit me, I wipe this, I will begin with what? Model. Then I have model. I have what we call model. Or less otherwise stated, or most of the time, this dependent variable is always represented with a capital letter Y. And the independent variable represented with a capital letter what? X. Or less otherwise stated. So in a simple linear regression, we have only one dependent variable and one independent variable in simple linear regression. So how do I now present the model of a simple linear regression? The model is written as that my y, which is the dependent variable, is given as beta 0 plus beta what? X plus what? E. We now say where this my y here is the dependent variable. Permit me to write as dv. Then this my beta 0 is what we call the intercept. The what? Intercept. Then this my beta is what we call the slope of the regression line. Of the regression line. This is intercept of the regression line. A regression line. Then this my x here, of course, is the independent variable. Permit me to write I, D, V. Independent what? Variable. And then this my E is what we call the error term. the error 10. So this is what we call the model for simple linear regression. Only one dependent variable, only one independent variable. And then this my beta 0, beta, described as the intercept of the regression line, and then beta, the slope of the regression line. And these beta 0 and beta are called the regression parameters. The regression parameters. So when they talk about regression parameters, they are making reference to beta 0 and beta. This is the model for simple linear regression. What becomes a model for multiple linear regression? What is the model? We come to the board. Of course, you see what we have on the board. This is the model for simple linear regression. This is the dependent variable at y. This is our intercept of the regression line, the slope of the regression line, the independent variable, and the error 10. So I clean and give us the model for the multiple linear regression. In the multiple linear regression, we have one dependent variable as well, written by what? Y. But we have more than one independent variable. It could be 2, it could be 3, it could be any number. Because we are not certain about the number, we can then say there are k independent variable or explanatory variable, where this k could take any value. So I have what is called what? My x1, x2 down to what? To x1 k. That is the first explanatory variable, second explanatory variable, down to the kth explanatory variable. All these variables, their values are being used to predict the value of this dependent variable y. How then do we show the relationship that exists between these variables with a regression model? It is written as that y equals my beta 0 plus beta 1 x1 plus beta 2 x2 plus up to beta what k, that is plus beta what k x what k plus error 10. This is a model for multiple linear regression where we have more than one independent variable. This is, of course, what we call, this x1 stands for what is called the first explanatory variable. This slope beta 1 now is talking about the slope of the first explanatory variable in relation with what? The dependent variable. The same thing applies to what? To beta 2 down to what? To beta k. And of course, like I earlier had mentioned, this y is the dependent variable. This is the what? The intercept of the regression line. This is the slope of the first independent what? Variable. This equally is the slope of the second independent what? Variable, down to the beta k, talking about what? The slope of the kth independent what? Variable. And of course, this my beta 0, beta 1, beta 2, down to beta k are what we call the regression parameters, or the parameter of the regression model, whichever way you call it. The regression parameters or the parameters of the regression model. That is what we refer that to be. Okay? Now, we are equally going to talk about what we call the regression equation. But before we talk about the regression equation, permit me to remind us that when we talk about the regression parameters or parameters of the regression model, We are talking about values that exist in the population. So for us to know the true values of these are beta 0, beta 1, beta 2 down to beta what k, we are going to take what samples or observations from the dependent variable y and then the independent variable x1 down to xk in order to estimate the value of these are beta 0, beta 1, beta 2 down to what to beta k. And because we are calculating their value from what? From their sample, we will be talking about the estimate of these values and no longer their true values. And that will now bring us to what we call the regression equation instead of the regression what? Model. Now for the regression equation, we are having something like this. For simple linear, we are having what? Y estimate is given as beta 0 estimate plus beta estimate what? X. We are no longer talking about what the error term. We are now talking about we have estimated the value of beta 0 and what? And the beta. And we have replaced it now into that regression model. And of course, on the course of doing this estimation, that error term will be dropped off or is taken care of. And what we have here becomes what we call the regression equation of a simple linear equation, or the equation of a simple linear regression. The same thing applies for the multiple linear regression. In the multiple linear regression, we are going to have what? That y estimate is given as beta 0 estimate plus beta 1 estimate x1 plus beta what 2 estimate x what 2 plus then plus what beta what k estimate of x what k. We no longer talk about what the error term. And this thing becomes what we call the equation for the multiple linear regression. For a multiple linear regression. Like I earlier had said, we are no longer talking about what the error term, because on the course of estimating for beta 0, beta 1 cap, beta 2 down the line, of course, that method of estimation brings that error term to what? To 0, and it is removed from what? From the model, and it becomes what? That equation. That is equation for simple linear, equation for multiple linear regression. However, before we can estimate these values and be able to have a value that actually represents a reliable values of the population parameters, there must be assumptions which our regression model must satisfy. Therefore, before we go ahead to estimate the regression parameters, be it from the simple linear or be it from the multiple linear, the model of our regression, equally be it simple linear or be it multiple linear, must satisfy some assumptions. So we are going to talk about the assumption of simple linear regression or assumption of linear regression, whether it is simple or whether it is multiple. So having understood what is called model, having understood what is called what? Equation, we are saying that this our model is going to satisfy some specified assumptions before our estimate for the population, for the regression parameters can be what? Reliable. So we want to discuss what we call the assumption of a linear regression. So permit me to clean here. Talk about assumption of linear regression. assumption of linear regression. Number one assumption says that our dependent variable must be a continuous variable. Our dependent variable must be a continuous variable. That is, that d dot v must be a continuous variable. Must be a continuous variable. Continuous variable. And of course, when we talk about continuous variable, we are talking about either what we call the interval or ratio variables. Interval or ratio variables. When we talk about continuous, this continuous, it could be an interval, it could be based on what? On ratio. The question becomes, when do we say that a continuous variable is an interval variable? Or when do we say it is a ratio variables? When we say that a variable is interval variable, it's what we are trying to say is that the difference between different quantities of that variable is meaningful. What we mean by meaningful is, consider for instance when you are talking about maybe a temperature of about 50 degrees Celsius and a temperature of about 90 degrees Celsius. The difference between these two temperatures or temperature measurements is actually very meaningful. And in that case, we are talking about what? Interval measurement under this continuous variable. But when we talk about ratio, equally, the difference between two of them is what? Meaningful. But then in addition, that zero measurement of that thing implies that that variable doesn't exist that place. That is having 0 degrees Celsius. That temperature there doesn't what apply. It has come to 0 degrees. Or that the measurement, simply put, that the measurement there of that variable doesn't exist. And not necessarily maybe using the example of 0 degrees. Just simply say that the value of that variable does not exist in that particular point where it has a measurement of what? Of 0. That is the number one property or the number one assumption of a dependent variable. Sorry, of assumptions of what? Of the model. Then number two says that the independent variable equally must be continuous. That IN or IDV must equally be a continuous what? Variable. Our independent variable equally must be a continuous variable. Then the third assumption there says that there must be a linear relationship between the dependent variable and the independent variable. There must be a linear relationship because we are discussing linear regression. There must be a linear relationship between the dependent and the independent variable. There must be linear relationship. Linear relationship between the d dot v and the I dot d dot what? V. And this linear relationship, it could be positive, it could be negative. And if it is what? Positive, of course, this kind of relationship can easily be shown using what we call the scatter diagram or what we call the scatter plot. That is, the scatter diagram is using what we call the XY axis to represent the coordinate values of the dependent and independent variable. For instance, I can represent this with y and represent this with what? With x. Here becomes what we call the values of what? The independent variable. Here becomes what we call the values of the dependent what? Variable. And when the value of this independent variable is given as this, the value of the other dependent variable is given as this, their intersection will represent with what? A point. And you continue to represent the values with a point till you exhaust all the data what? Points. Okay? And then when you have something like this, of course you can use a line to join. If it continues this way, you can use a line to join this way. And in this case, you have what we call a positive linear relationship. And in this kind of positive linear relationship, the slope is positive. Because slope, of course, means change in y all over change in what? In x. That is to say that if you want to measure the slope, you come and pick a point, draw it down here, draw it down here. You can talk about your x1, talk about your x2. Equally draw from here to here and draw from here to here. You talk about your y1 and talk about your y2. And of course, our slope here, slope equals change in y all over change in x, which becomes what? Y2 minus y1 all over x2 minus what? X what? Y. And because here the value of y2 is greater than the value of y1, equally the value of x2 is greater than the value of what? Xy. This quantity is going to be what? Is going to be positive. And we talk about positive linear relationship. This assumption must be satisfied that there is a kind of linear relationship that exists between the dependent and independent variable. You can equally have another one that appears this way. Permit me to clear here. You can equally have another one that appears this way and this way. Here still remains my y. Here still remains my what? My x. Here is my x. And I have this arrow here. And you begin to have something that goes this way. Begin to have something that goes this way. Where you have a line, a straight line that runs this way. It is still a linear relationship. But in this case, it's not a positive linear relationship, but a negative linear relationship. And here, slope is what? Is a negative. Because if you come here, if you want to take the slope, you make a point here and you make a point. Any two places in the straight in the line on the line. Then you draw it down to here, you draw it down to here. Here becomes what you call your x1, here becomes what you call your x2. Then in this case, you now have, because when it was x1 here, look at my y1 here. So here is my y1. And then when it was x2, look at my corresponding y2. So when we talk about change in y here, all over change in x, we are talking about y2 minus y1, all over x2 minus x1. But this y2 is smaller than the value of what? Of y1. So when you say this value here minus this value here, it turns out to be negative. And then that will make this slope what? Negative. And here you should be talking about what? Negative relationship. Though it is still linear and it satisfies what we are talking about here. Okay? So this is what we mean by that there must be a kind of what? Of relationship, a linear relationship that exists between them. Okay. Permit me to clean here. Number 4. The fourth assumption says there must not be any significant outlier in the data points. No significant outlier in that data point. What do we mean by an outlier? An outlier is the value of a response variable that is much larger or smaller than the values predicted by the model. So when there is a particular value of the response variable that is too large or too small from the values of that response variable predicted by the regression model, we call that particular data point or observation an outlier. And how to show this outlier here? You can have something here, you have a line, our scatter diagram equally. Here is talking about y, here is talking about what? My x. And maybe you have a line that goes this way, you have a line that goes this way, you have a line that goes this way, you have a line that goes this way. Then you have your line this way. Meaning that all the data points cluster around the line. All of a sudden, you have a particular data point here. Or all of a sudden, you have a particular data point here. Or all of a sudden, you have a particular data point here. So all these values are far away from this line. And we refer these values now to be an outlier. So this and this and this. So we are not expected to have these outliers. Because if you happen to have them, it is going to affect our estimates. And once it affects our estimates, definitely it is going to affect our model, which will not give us a better prediction. So the significant effect, or what we call the negative effect of the outlier, is that it affects our estimates, which in turn affects our what? Our regression equation or model. That is the fourth assumption. Okay, so permit me to click. Another assumption is saying that the observations must be independent. The observations must be independent from one another or from each other. That is, the value of a data point doesn't depend on the value of the other one. They are independent of what? Of each other. The observations. And then the other last assumption says that we should check whether our error term from the regression model is going to be normally distributed or approximately normally distributed. Or what we say, checking whether the residuals is going to be normally distributed or approximately normally distributed. The question is, what do we mean by residual? Residual is the vertical distance between a data point from the regression line. For instance, when I have this and I have this, I have this to be y, I have this to be what? To be x. And I have a data point, I have data points this way, this way, this way, this way, and this way. Then I have my regression line here. Here is a data point. The distance from here to here, the distance from here to here, from here to here, from here to here is what we call the residuals. The vertical distance between a data point and the regression line is what we call the residual. And we are saying that when all these residuals are collected, which is the vertical distance between all the points and the regression line, that it is expected to be normally distributed or approximately normally distributed. These are what we call the assumption of the is what we call the assumption of the linear regression. Assumption of the linear regression. Okay, what we're now going to do now is we're now going to go into having understood what is called the regression, having understood what is called the simple regression, having understood what is called the linear regression, having understood what is called the simple linear, having understood what is called the multiple linear, having looked at what we call the assumptions of the model. We want to go into what we call the method of the estimation of the regression model. So permit me to clean here. There are different methods of estimating parameters in statistics. Different methods through which we can estimate parameters. Then we have what we call the use of ordinary least square method. Then we equally have what we call method of moments. Method of moments. And then we have what we call method of maximum likelihood function. Method of maximum likelihood function. Method of maximum likelihood function. On the course of the study of linear regression, we are going to pay attention to the first one that talks about ordinary least square method. So we are now talking about estimation of the regression parameters using the ordinary least square method. What is this ordinary least square method talking about? It is talking about that the use of that method to estimate the regression parameters minimizes the sum of the square residuals. It minimizes the sum of the square residuals. Or what we call, it minimizes the sum of the square errors. Errors and residuals are the same thing, and they can be used interchangeably. So that is actually what this method helps us. It minimizes the sum of the square residuals. And by the use of this method, the estimates for the intercept and the slope of the regression model is given as. So permit me to clean here. When we use this method to estimate for the intercept, which is beta 0, and estimate for what for beta, which is what is the slope, their formulas can be given as this way. We have that my beta cap, I am now talking about estimates, is given as n summation of x, y, minus summation of x, summation of y, all over. We have n summation of x squared minus summation of x, all squared. Can be given that way. Okay? Or we can equally say that, or we now say that our beta 0 cap is given as, we have what we call y bar minus beta what cap x bar. Of course, y bar is talking about mean of the response variable, which of course becomes summation of y all over what? N minus Beta what? Cap. X bar is what? Summation of x all over what? N. So when we use the ordinary least square method, we'll be able now to drive the formula for beta cap, which is the slope, to be this, and then beta 0, which is the intercept, to be this. Therefore, given data points for x and y, we just need to get the product of x, y, then get the sum of x and sum of y, square the observations now here to be able to evaluate this, and then down the line. This is what we call the estimate of the regression parameters in terms of the beta, in terms of the slope, and in terms of the intercepts. So permit me to claim here. And of course, when the value of this must have been obtained, one comes, and then in that model you had earlier, you are going to have that y estimate is given as what? Our beta 0 estimate plus what? Beta estimate of what? Of x. And here we are talking about the dependent variable, which we have estimated its value. Then here is talking about what we call the intercept. And of course, the intercept is the value of the dependent variable when the independent variable is 0. So because when here becomes what? 0, if you say that this beta estimate multiplied by this 0, it goes, and you have that y cap is equal to this. So the intercept is the value of the estimate of the regression what? Line when the independent variable is what? Is 0. While this slope, which is the beta, is talking about the amount of change in the dependent variable that is caused by a unit increase or decrease in the quantity of the independent variable. That's what we call the slope. The amount of what? Increase that is caused in the dependent variable by a unit increase or decrease in the what? In the independent variable. That's what we call the slope and what we call the intercept earlier. Okay, having understood what we mean by regression and the rest of them, and having understood to the point of what we call the equation and even the model, how certain are we that this model which we have developed for this linear regression will be able now to estimate all the variations that exist in our response variable? How do we know whether this our model or this our equation is capable to predict correctly the value of our dependent variable, given the value or given the estimates of this intercept and this slope? And that will bring us to another thing that is called coefficient of determination. Coefficient of what? Determination. So let us discuss about coefficient of determination quickly before we take a small example on this. Coefficient of determination. Of determination. Okay? Of course, when we talk about coefficient of determination, we are talking about the measure of the variations in the response variable that is accounted by our model or by our independent variable expressed in percentage. That is the percentage variations in the response variable that is accounted by our regression model or by our independent variable or variables. That is what we mean by coefficient of determination. And it is often represented with what? Capital R raised to power what? 2. Coefficient of determination. Okay? Therefore, when we talk about variation that exists in the dependent variable, we can see clearly there are different kinds of what? Variation that can exist in the response what? Variable. The variation that can be explained by our model and the variations that cannot be explained by our model. So there are two sources of what? Variations there. And these two sources of variation there is what we say explained variation and unexplained variation. We have what we call explained variation, explained variation, and what we call unexplained variation. Explained variation, of course, is talking about the variations in the response variable that is accounted for by our model or by our independent variable, and is often represented with what we call S what R, sum of the squared regression. Sum of the squared what? Regression. Then when we talk about unexplained variation, we are talking about the variations that exist in our response variable that is not captured by our model or by our explanatory variable. So the sources we do not know where they are coming from. It could be as a result of other independent variable influencing that response variable which we did not take into consideration in the research. It could be the influence of weather or anything in our experiment, interfering with the values of what of the response variable. So we don't really know where they are coming from. We call it what? Unexplained variation. And then it is always represented with what? S what? E. Sum of the squared what? Error. Therefore, all the variations that are existing in our response variable can either be explained by the model or it cannot be explained by what? By the model. So the total variation there is SSR plus SS what? E. So the total variation there, which of course I'm going to represent with what? TSS. That is total sum of variation or total squared variation. Total sum of squared variation, sorry. Total sum of squared variation is given as S what? R plus S what? E. And of course, our coefficient of determination is defined as the ratio of the explained variation all over the total variation. That is the coefficient of determination. That my R squared is given as my ratio of explained all over ratio of the total variation. Explained variation all over total variation. That is S what? R all over TSS. That's what we have there. And of course, from this equation we have here, we know that our SSR here, SS what? R, is given as what? TSS minus SS what? E. Of course, when we write TSS, some people can say SST, sum of the squared total sum of squared. So do not be so confused when you see people write SS what? T. Talking about sum of the squared total. can equally be said total sum of what? Squares. Okay? So in that case, when I come here, then of course I know that this is expressed as this. So I can equally come here. In place of this SSR, I am going to put this. And what I have becomes that this equals. I have what? In place of SSR, it becomes what? TSS minus SS what? E all over what? TSS. And then, of course, this thing becomes what? TSS all over what? TSS minus SS what? E all over TSS. So that this can cancel this to give us what? 1 minus SS what? E all over TSS. So the formula for coefficient of determination is given as this. 1 minus the ratio of sum of squared error to total sum of square or sum of the squared total. Okay? So for us to be able to calculate the value of a coefficient of determination in this context, we must be given sum of the squared error, we must be given sum of the squared total. And in that case, we can easily calculate it. So if someone says sum of the squared error is 5, and then maybe sum of the squared total is something like 9, you'll be able to say 1 minus 5 all over 9 to get your coefficient of determination. And because we are talking about the percentage of variation that can be explained by the model, we now find out that the higher the percentage that can be explained by our model, the better the research. So the higher the value of the coefficient of the determination, the better fit our model has to predict the values of the dependent variable. So values closer to 100 is better than values closer to 0. This is because it is expressed in percentage. If it's not expressed in percentage, we are talking about values from 0 to 1. So the values closer to 1 now becomes better than the values closer to 0. So when we calculate this coefficient of determination and we get that our R squared is equals like 65%, for instance, we are trying to say that 65% of the variations in the response variable is accounted for by our model or by our independent variable. So in that case, 45% of the variations there, we cannot account for them. We don't know the sources where they are coming from. Okay? So that's what we mean by coefficient of determination. However, when we are not giving sum of square error, we are not giving sum of the squared total, we are giving raw data. We have a way of getting the value of a coefficient of determination. And I usually call that particular formula the computational formula for coefficient of determination. So for coefficient of determination now, I can write something like this. That's for the computational formula. Permit me to clean here. This is just what we arrived at. So for coefficient of determination, we can talk about what R squared is given as. We have what? Beta estimates. Then we open a bracket. We have what? N summation of what? X all squared minus summation of X all squared all over. And summation of Y all squared minus summation of Y all squared. We close this bracket here. Okay? So I think this beta I'll cross check is either square. I think so. But I'll cross check it. So that is what we call coefficient of determination. Okay? Now, once we are given data, of course, we know what is called our x, the values of independent variable. We square it. We know the value of our x. which is independent variable, we sum it before we now square. And with that, we'll be able to get the value of this. So what are now the importance, or what we call the properties of our coefficient of determination? The property of coefficient of determination is, number one, it helps us to determine the adequacy of our model. It helps us to determine the adequacy of model, or to determine how well our model can predict the value of the dependent variable. That is number one. Number two, it is used as a goodness of fit test. You are talking about your model being fit. And we are saying that we use the coefficient of determination now to check how this model is, the capability of this model to predict our response variable. Therefore, it can be used as a goodness of fit what test. So when you have a model and you can determine the coefficient of determination there, you can equally use the value of that thing as the goodness of a test what value, to tell people how that model which you developed for that particular data and research now is. And of course, we say that the value of the coefficient of determination lies between 0 and 1 inclusive. If it becomes 1, which of course it is very rare, practically impossible to become 1 in real life situation, because there must always be variables or variations in the response variable which cannot be accounted for by our model. And it is also very rare for it to become what? 0. Because definitely our model must be, unless the assumptions are not satisfied, and there are so many other mixed up now in terms of whether there is a linear. In fact, if the assumptions are not met very well, that's when we begin to have values that can maybe become 0, which is of course very, very rare. So it is a value that is between 0 and 1. And then one good thing about this coefficient of determination, it can be used for what? For simple regression, it can be used for multiple regression. When it is used for simple regression, the coefficient of determination becomes that my R squared, or my R, equals what we call R squared. Coefficient of determination R becomes what equals what? R squared. And when we talk about this coefficient of determination here being R squared now, and we talk about R, I am going to say where this particular R that is here, is talking about the correlation coefficients. The correlation coefficient. Let me return using this capital letter, please. Let me using capital letter, talking about coefficient of determination. When we are talking about simple regression, okay, that is when there is only one independent variable and one dependent variable. The coefficient of determination is the square of the correlation coefficients, R. So if this R here stands for the correlation coefficient in a simple regression, the coefficient of determination means the square of that. So if the value for the correlation coefficient is something like 0.05, the coefficient of determination in that place should be 0.05 all raised to power of 2. That's what we have in that particular place. Okay? Then we now go over to what we call the correlation coefficients. Explain something about the correlation coefficient very quickly. In the regression, we talked about predicting the value of a response variable or an outcome variable from the value or values of other variables. So for you to predict the value of a variable from the value or values of other variable, there is a kind of relationship that exists between these two sets of variables. Because if they are not related, there is no way you can predict the other value by changing the value or values of other variables. So there must be a kind of what relationship. So in correlation, we are looking at the degree of this relationship that exists between these two or more variables, or the strength of the relationship that exists between these two or more variables, or the extent of relationship that exists between these two or more variables. That is what we do in correlation. So another concept we are talking about here quickly, in order to manage the size of this our class, is what we call the correlation. What we call the what? The correlation. Correlation. The correlation. The measure of the extent, or what we call the degree of the relationship that exists between two or more variables. That's what we talk about in a correlation. Of course, when we talk about correlation, we are talking about, like I earlier had said, the extent of what relationship existing between two or more variables. And there are two formulas with which to obtain what we call the correlation coefficient. The correlation coefficient is that numerical value that tells us the extent of the relationship between two or more variables. There are two major formulas that we use to obtain those values. And those two formulas are coming from two persons called the Pearson moment correlation coefficient and the Spearman's correlation coefficient. The Pearson correlation coefficient is given as this. That is Pearson moment correlation coefficient This Pearson moment correlation coefficient, of course, represented by what? R will be given as R, you can say R subscript xy. If you are saying that the independent variable is x and dependent variable is what? Is y. Okay? Then this is given as n summation of x, y, minus summation of x, summation of y, all over square root of n summation of x squared minus summation of x all squared, open a bracket, close the bracket, open again. And you have n summation of y. Oh, sorry, there is a glitch in power. So we continue this when my power is restored. Sorry for that.